Hello everyone. Here I introduce our work, Geometry-Aware Hierarchical Bayesian Learning on Manifolds. The main problem we try to solve is how to effectively and efficiently use Bayesian learning methods to analyze 3D manifold-valued data. We care about the two applications. The first one is nonlinear dimension reduction on manifolds. The second one is feature aggregation on manifolds. One of our most important achievements in this work is a new kernel. Considering the uniqueness of the manifold-valued data, we stress two properties of this kernel, the geometry awareness and intra-kernel convolution. The theoretical motivation of our kernel comes from two observations. A takeaway of these two observations is if we can find a proper diffusion process and solve this diffusion process to get an analytic solution, we may define a qualified kernel from the analytic solution. So in this work, we take the periodic potential diffusion process as the target problem. The periodic term in this diffusion process could help us to simplify the computation of the integral. So in this problem, we can transform the integral to the summation of two special Fourier transforms, a cosine transform and a sine transform. By solving these two special Fourier transforms, we can get an analytic solution to the periodic potential diffusion process. Then, based on this analytic solution, we define our geometry-aware convolutional kernel, the GAC kernel. Noting here, because the diffusion process is a dynamic process, so we use the additive kernel form to define the GAC kernel. So in the paper, we also provide a completed theoretical proof of the two properties of our GAC kernel. So furthermore, we summarize all this process into a theorem, which says the periodic potential diffusion process stands for the family of kernels, just like the family of a Maton kernel. So we designed 3 experiments to address the two applications we care about. The first experiment is called unsupervised ceiling point selection. The target of this application is trying to extract some ceiling points from the given shape. The ideal selection should be evenly distributed in some high curvature regions or the region of interests. So here we use different methods, different kernels to try to extract the ceiling points from 5 publicly available data sets. So we can see that our methods can constantly extract meaningful and reasonable ceiling points from the given sample. The second experiment is called human pose retrieval. In this experiment, we introduced the hierarchical Bayesian network to try to aggregate features from the given dataset. So for each sample, we extract the ceiling points, and we organize all the features on the ceiling points to the input feature space, and then use the hierarchical Bayesian learning to aggregate these features. We tried fixed and unfixed Bayesian network to test the performance, and we can see that the network using our method gives the best accuracy. The final experiment is called point cloud classification. We try to incorporate a neural network to learn the features and feed its features into the Bayesian network to do the feature aggregation. The experiment shows that the combination of neural network and Bayesian network yields the best solution. Thank you for your attention.